Now the first topic that I'm gonna talk about today is probably using Clojure to do functional programming. So when we talk about functional programming, most people will say, oh, Monads. Let's talk about how to use Clojure to write Monad. And then it's a pretty useful skill, actually. I'll say that it's like a software design pattern, except that it's very powerful. Let's get started. The operating system that I use is OS X. The editor that I'm using is SpaceMax. I like this setup because it's very minimalistic. I don't need to spend a lot of time to play with how to configure my Emacs, and I don't need to spend a lot of time to twinkle with the operating system. Everything just works out of the box. So Monads. I'm trying to answer these three questions. What are Monads? Why do we care as Clojurist? And can we understand it without knowing those fancy types? This tutorial is inspired by Conrad Tinson's Monad tutorial. It's a very good tutorial, and it has 4 parts, and it covers more topics. But I found that using this repo style to introduce Monads is more visually easier to understand for beginners. So let's get started. Let's try to make the font bigger. So first, how do we assign values to names without defining stuff in the global space? As you can see, defining values in the global space is side effects. Functional programming is all about getting rid of side effects. So let's say that we have these anonymous functions, and we try to assign these values to the names. And you can see that the first function, we take the parameters of a, assign the value of 1. We try to assign the value of 1 to a using this anonymous function. Basically what it says is we define an anonymous function, it takes a, and then we apply the function with 1. And then within the first function, we try to bind another value 2 to the name of b. So we do the same thing. We define another anonymous function, and then we assign the 2 to the function. And now we have a equals to 1, b equals to 2, and then we can perform our final computation, a plus b, and the result evaluated to 3. Pretty simple. Now this is pretty ugly. Can we make it better? For example, like, can we not do this weird stuff where 1 and a are spread from each other pretty far away, and the more steps of computation we have, the further away the name and the value will be. This is not good. Of course we can. So let's say that we define these 2 functions. The first function is mBind. Basically just takes a value and a function, and it applies the value to the function. And then we have the end result. It just returns the same value that passing. This is same as the identity function. So we have these 2 functions, mBind and end result. Some people call it monadic bind and monadic result. It's basically the same thing. And now that we have these 2 functions, we can do this. We can mBind a value to a function with the reverse order. And the second step is the same. We mBind another value to another function. And then finally we can have our final computation of end result, a plus b. So we bind a to 1, we bind b to 2, and we have a plus b, which is 3. This looks better. You can see that the name and the value are close to each other, and they are on the same line. But what is this to do with monad? A monad is exactly this. 2 basic functions, or a set of operations, the monadic bind and the monadic result. Now we have these specific types of monad called identity monad, which has a monadic result and monadic bind. The monadic result is an identity function, and the monadic bind again is have some identity characteristics. I'll explain later. So of course the mBind still not looking good, because you can see that even though the names and the values are close to each other, they are within the different scope. We still have this separation between the name and the value because they are within different functions. That's where macros come in. As a Lisp, we have the power of change our semantics. So we define this run monad. The run monad is a macro that given a monad. What is a monad? Monad is two functions, remember? The end result and end bind. So this is exactly what this monad is. And then, given those steps is a pairs of names, we call it var, and values, we call it val, and it's a collection of these pairs. And finally, we have our end expression. That's basically is the final expression. So when we have the steps as a collection that is not empty, we do the end bind recursively. This is just templating, but all it does is end binding function to the values recursively until we reach the last step. When the step is empty, we'll be going into the ending condition of having the end result apply to the final expression or the final computation. And let's see what this does. As you can see, we have the identity monad, which is again the end result and the end bind functions. And now we can assign the values to the names in a very convenient way, and it looks very clean and nice. And let's see what this actually is. And what we can do is we use macro expand. We can see that basically it's the same thing. It's binding the function with the value and apply it to another function under the context of the identity monad and do it recursively. So you can see that this is exactly this. Trying to make a match. So end bind 1 function, end bind 2 function, and then end result final computation. Same thing. End bind under the context of the monad, which we define here globally. Apply 1 to the function, which names the value as a, and apply 2 to the function having the name of b, and finally the final expression a plus b. So you can see that it expands to the same thing. Looks familiar? Yes, this is exactly the same as the Clojure let form. So what is Clojure let? Oh, it's just run monad under the context of identity monad, which means you're giving values names. That's identity. Make sense? Now let's introduce the algo monad library. It's a Clojure library. It's very minimalistic. That is very easy to understand and very easy to extend if you want to change it. The feature is a little bit lagging. It's a good library if you want to learn about monads, but there are better libraries out there that if you actually want to use monad to help you with production systems. We'll talk about that later. So you can see that the algo monad basically is just same thing, do monad. We call it run monad, but they're the same thing. Identity M, which is, remember, the identity monad, which has two functions or two types of operations. And let's go into the library and see what it is. Oh, it's just end result and end bind. End result is identity, which takes a value and returns the value. This is exactly what we have done. And it evaluated to 3, same thing. Now let's look at the maybe type. Let's assume we want to perform 3 steps of computation. First computation is some super duper computation, but it will fail and returns the $1 billion mistake, a null pointer. And then we have the second step of computation that relies on the first computation, but it also does some expensive computation. Here the computation, let's say that it takes 5 seconds. And finally we have our final computation, which relies on the first 2 computation results and plus 42. And let's see what this does. You can see that it takes a long wait, around 5 seconds, and then returns the null pointer exception. Let's say that for these types of computation, we can have a maybe monad. And maybe monad is basically an identity function again as the end result, and monadic bind function which applies the f with the value v, except that this time, if the value is a null, we will not do anything. Only if the value is not null, then we apply the f function. So you may ask, what is the meaning of the function f here? The f basically means the rest of the computation. So you can see that the mBind function got executed between each steps of the computations. So by defining the monadic bind function here, we can programmatically control what will happen for each step of the computation. This is a very powerful heuristic. Let's see what this will do. Again, run monad. This time we use maybe monad. And same thing, first we do the super duper computation which will fail and returns the null. And then we have another step of computation which relies on the previous computation result. And also, it takes around 5 seconds to finish. And finally, we have plus 42, a point on the previous computations. You can see that it evaluated to the result null instantly. We are not paying the price for this expensive computation here, which takes 5 seconds. We also don't use the previous failed computation returning the new value here and apply trying to add 42 to this new value. How magical. This is the power of monadic bind. You can see that for each steps of the computation, we check the new value. If it's new, we simply do not apply rest of the computation. Amazing. Again, the algo monad library has the same thing. Do monad is the run monad. Same thing, it's just different names. Maybe m is basically the two sets of operations. And we can ignore the m0 and m plus right now. We don't use it. The most important thing is the m result and the monadic bind. And you can see that same thing, we perform the new check for the monadic binds. And let's evaluate these instant results. Now, let's think about what is the monad again. As you can see, the monad here is about the monadic bind, right? And I said the f represents the rest of the computation. If you heard of the term continuation, that's the same thing. A continuation is the rest of the computation at certain point of your program. A monad within its monadic bind. The f here is the rest of the computation, except that the monadic bind is executed for each step of the computation. That's why it's so powerful. That's why people call it the programmable semicolons. But you might ask, so all you can do is you insert computations in the sequential of computations. That's not very useful, right? I'll say no. I'll say not only that the monad can be applied computation in a sequence manner, it can also achieve nonlinearity. What is nonlinearities? If you are doing tree traverse, you can see that each branch of the node can be traveled, and to travel all the nodes, the size of your travel will become exponential. So let's see sequence monad. Sequence monad is again two functions. M result is the monadic result. This time we have list. That means instead of identity function, we always returns a list. And also we have the monadic bind. What does the monadic bind do? The monadic bind basically applies the function f, the rest of the computation, to the value v. And this time we map the rest of the computation f to the value v. What is v? V has a type. The type of v is a list. That's what the m result means. It defines the type of the value of the topic here. And then after we compute all the rest of the computation on each value of the v, we flatten the list into a single list instead of list of list. Let's see what this do. We have a value of a list of 5 starting from 0, 0, 1, 2, 3, and we bind this value to a. So a is a list of 5 numbers starting from 0. Same thing here, we have a list of a, and we bind the list of a to b. Remember, a is the result of the first computation, which is 5 numbers. Keep that in mind. And finally, we plus a and b together. Let's see what this does. Oh, we have 1, 2, 3, 3, 4, 5, 4, 5, 6, 7. So we are not just doing 5 computations. So we are not just doing 2 steps of computations here. It appears that we are doing 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 computations here. How is that? Let's try to trace this down. Let's print out the value of v here. And let's fire up our useful repo. And let's perform this computation again. You can see for the first step, we have the value as the 5 numbers. And then for the second step, range A. The first of range A is an empty list. Why is that? Oh, it's because the first element of the list is 0, and range 0 is empty list. And then for the second element is 1. Range 1 is 0. Range 2 is 0, 1. Range 3 is 0, 1, 2. And range 4 is 0, 1, 2, 3. Oh, so this sequence monad is not linear. It's a nested loop. It performs the second steps of computation on each element of the previous step. Again, the algo monad version is the same thing, except that this time you can see that we actually use the end result function. Why is that? First of all, we have 5 elements, and you can see that the difference of the second step of computation is that instead of making another range or list of numbers, we just return +1 of a, and that is a number. And remember, for each step of the computation, we are expecting the value of v to be the type of a list. So that's where the end result, the monadic result, comes in handy. We can always apply a value with this end result and returns the list type. So now the types are in line. So we can see that for the first step, we have 5 elements. For the second step, we increment the value of each element by 1. But we are returning a list, so we are not breaking the monadic rules, or some call it the monadic laws. And now, you might seen this form before. A for, some people say it is a loop. For each a in the element of 5, right? But then again, the second step is a sequence monad, and it evaluated to the same thing. So this is not a single layers of loop. It's an nested loop, or also known as the sequence monad. So finally, why do we care as Clojurist? Because monad is everywhere. People are using it without knowing it. A lot of people are using for. A lot of people are using list comprehensions. A lot of people are using maybe type. Some language call it optionals. And we are definitely, everyone is using the let form. So how do I learn to use it? Pretty easy. We have this repo system like Clojurist, and we can learn any language concepts using the repo. You can repo this exercise and have fun. And there's more useful types of monads like error monads. So instead of the maybe monad type, we can have the error message stored in the monad itself, so that when things go wrong, we know what exactly is wrong. And we can have the trial monad. Basically, we try each computation, and if we catch an error, we wrap the error like an error monad and pass it down, so that we have the exception handled by the monadic bind function. So we don't need to try catch every time we call something that might fail. And then monad transformers are interesting. They combine two monads together. For example, for the sequence monad, for each steps of nonlinear operations, it might still fail. What if we want to wrap the failure using an error monad? That we can use a monad transformer to combine the error monad and the sequence monad. So again, you can check out this presentation using this repository and feel free to ask me questions about it. Thank you for watching.